All right, hello physicists. So the other day you worked on this simulation where you filled out the yellow highlighted spaces on the sheet here. So in order to look at the rest of the circuit, we'll have to look at each individual segment. So the ones, the twos, the threes, and the totals. And we should see that to find that missing voltage or potential difference, there is a relationship between the resistance, the voltage, and the current over every single segment. And that relationship is Ohm's law. It is in your reference sheet, commonly known as V equals I times R, potential difference equals current times resistance. On your reference sheet, it's actually written as the following. Current is equal to change in voltage over the resistance. And they write it in terms of current for a pretty good reason. By changing the voltage or the resistance, you are then changing the current. So if you think about a battery, if you increase the potential difference of the battery you're using, maybe you go from a AA to a D battery, what's going to happen to the current? Well, it's going to increase. Those electrons will travel at a faster rate. We'll see a higher current. On the other side of it, if you increase the resistance in the current, it'll have the opposite effect. It will actually slow down your current. So Ohm's law is rather easy to use. You might see it as an example like this. If a student measured a current of 0.1 amps and a voltage of 5 volts across a light bulb, what is the resistance of the light bulb? So very simple numbers here. Oops. So I'm given the current, which I can write as I. Come on. This is not going to work. Here we go. Current is 0.1 amps. Our voltage is going to be 5 volts. And we are looking for the resistance. So this is nice and lovely. I can use Ohm's law. We can write it as V equals I times R. Isolating the R, we know that's going to then be V over I. And when I plug in, I simply have 5 volts over 0.1 amps. Numerically, that comes out to be 50, but the unit for resistance, remember, is ohms. The symbol is omega, but it's pronounced ohms. So knowing how to use Ohm's law is very important when looking at circuits, but it's not the only thing we have to worry about. Okay, the other main concepts are then the patterns we see between series and parallel circuits. So on your handout, you're now able to use Ohm's law to complete the missing pieces. And once you are done with that, you should see that there are definite patterns in the resistors, the voltages, currents with series, and a different set of patterns in parallel. To summarize that, we can take a look at this slide here. So I highly recommend you memorize this. There is an equation for the resistances on your reference sheet, but otherwise you don't see this anywhere. So you'll need to memorize it. And the idea is rather simple. In a series circuit, your currents are all going to be the same across every single resistor, which makes sense because in series, you have one single flow of electrons. So that current will be the same throughout the whole deal. Potential difference is your battery source, your V total, is only in one location. And as you go across each voltage, you get what's called a voltage drop. So if you added all the voltage drops, they should equal what you started with as your original potential difference of your battery. All right? When you add resistors in series, they also add. The more resistors, higher total resistance. Parallel is a little different, all right, because in parallel circuits, you have different branches. Each branch has its own current, okay? But if we were to add the currents across each resistor, add them all together, we should see that that is the total current of the circuit. So no current is lost, no current is gained. It all came from what you started with. Again, because we have each different branches, that battery is going to supply the same amount of voltage across each branch. So all the individual voltages should equal the total. Here's where it gets funky. When you add resistors in parallel, your total resistance actually gets weaker, which is very, very strange. So that's why I hope you saw that in the simulation to show that the more resistors in parallel actually increases your current.